A divided by C of k at least. So there is a positive proportion of A. Which is intersected by a coset of the Russian. Okay, so this is the main theorem. So it's a weak form because there is a stronger version with a better description of sets A of this form. Sets A satisfies A times A less than K times A. But for example, for the purpose of establishing Gromov's theorem, this is enough. And the proof of this is, is already substantial. So, some remarks. So, in fact, we will show that the nilpotency class and the number of generators of the normal nilpotent subgroup of H, finite index of H can be bounded quite explicitly in terms of K. So there's a good bound on this data. Second remark is that I could have formulated the theorem a bit differently. I could have said, so the theorem is equivalent to the conclusion of the theorem is equivalent to say that there exists H such nilpotent such that A is contained into X times H which way did this and there is X in G, a subset of size at most 1. So in other words, you can cover A by a bounded number of cosets of H. So I should just make it because I decided the left coset here. So clearly, if this is true, then there is a coset positive proportion. But you see, the other way around is also true, because this is so. You see this. Note that so this is the key word is Hrushovski covering. So those who remember the took from previous lectures, but it's really a simple argument. So if you look at A intersected with XH multiplied by A, this is less than A times A, so it's less than K times A in terms of size. So what you can do is you can take the maximal subset of translates of this guy here, maximal collection of these joints. translates AI belongs to A. Since it's maximal, so you take in one derivative k, it's maximal. So this means that k is less than c of k times k. And so you see that for every a now in A, this translates must intersect one of them. Because of the maximality assumption. And so this means that you can write A as an element of this form. So, but this is contained inside H. Okay. So this means that all of A is contained in a few in boundedly many cosets of H. Okay. So the two things are.
Can one replace such an nilpotent by nilpotent by eventually increasing the constant set K?
No. No. So you could have, for example, a large finite group, simple group, finite simple group. Satisfy this hypothesis with k equals 1. And a large finite simple group does not have any bounded index. In the stronger form of the theorem, we show that the virtually nilpotent can be replaced by finite by nilpotent, where the finite part belongs to a small power of A. So belongs to A union A inverse to the power 12. So this. So in some sense, if the finite part is large, it's because of A. A is large because A contains a large. So finite. I keep going with those remarks. So, remarks. So, in fact, in the proof, we put the theorem in a special case. So it's enough. We put the theorem. When A is a K approximate group. So K approximate subgroup of V. So what does it mean? Let me remind you. So this means we assume that 1 belongs to A, that A is symmetric, and that A times A is contained in boundedly many cosets of A. And we translate something. Okay, so any set of this form, of course, satisfies the hypothesis that A times A is less than K times A. But we saw in the second lecture that doing some combinatorics, a bit more delicate than what I just did, but of a similar flavor, that any set of this form, A times A less than K times A, contains a set A prime, which is a positive proportion. There's some explicit proportion of A, with the property that A prime union, add inverses, and you add 1, and you take the third power, then this set B is an approximate group. So it satisfies symmetric, and it satisfies this covering property. So if you can prove the theorem for this B, and also show that this B is not much bigger than A itself, so it's less than K times A. So if you can prove the theorem for B, that it's contained in a few cosets of some H, then it will be true for A as well. So the advantage of working with those sets is that it's somehow, these properties are nice to have. They are easier to handle than the definition in terms of cardinality of the product. Okay.
I have a question about the previous remark. So, how far H is from nilpotent depends only on the size of A, not on A. This is what you meant about this simple. So, in the strongest form, you said finite by nilpotent, and this finite only on the size of A, not on A.
No, yeah, the finite part, so this H will actually be of the form K times L, where K is a normal subgroup of H, K is finite, L is nilpotent, and K is contained in A to the 12. So, yeah, that's what I meant. Yeah, so in this weak form, the theorem does not apply to finite groups, but in the strong form, it does apply to finite. G is finite. Okay, so, right. Another remark. It's like if G has finite exponents. So today I will prove the theorem in the case, in particular, as a corollary. So I will prove a result which is called the Hrushovski-Lie model theorem, which implies as a corollary a special case of the theorem in the case when G has finite exponents. So if G has finite exponent, i.e. there is this integer E such that G to the E equals 1, which is E, then you see from the theorem that H must be finite. Because a torsion, every finitely generated group has a torsion-free subgroup of finite index. So if every element is torsion, then it must be finite. So this means that the conclusion means that A is contained in a bounded number of cosets of a finite group. Finite subgroup, which itself may be large. It could be a large finite subgroup of G. Maybe I keep showing it. Or, yeah, maybe I keep. Okay, so the strategy of Prof is a bit like in Gromov's theorem. So yeah, so let me talk about the products. So the theorem, I mean, we can use ultra products, and that's what we did, to use ultra products for the theorem. Hrushovski was not using ultra products in his paper. He was using the language of model theory, which is a much more powerful and conceptual language, which allows to which is much more sophisticated. So ultra products are, in some sense, the model theory of the poor, the model theory of, if you just, it's a way to quickly put your hands on an object which model theorists don't care to consider because they don't want an explicit construction. When they say that they pass to a saturated model. And but I'm going to be more down to earth, even though I think there is great value to think in terms of model theory, but it requires some experience. So ultra products, on the other hand, also require some experience, but you can maybe more quickly arrive to understanding. So you start with ultra products, ultra filters on the wheels, on the natural numbers. So let me remind you what this is. So there are various ways to say. So it's finely additive 0, 1 value matter defined on all subsets of n, so that's a very good way to think of it. Another way is to think of it as a family of subsets of n with the following property such that following axioms of the filter. So if A and B belongs to U, then it's stable under intersection. A is separate B, it belongs to U. If A belongs to B and A belongs to U, A is in B, then U is in U. You don't want to assume that the empty set is in U. It's not in U. And it's non-empty, so you assume the entire set is in U. And so this is a filter, and you want that besides U is maximal for this question. This is an ultra filter, and we are going to require that U is non-principal. So this means that singletons are not in U. So the way these are obtained by applying Zorn's lemma to find a maximal set, you start with a filter and you find maximal one by Zorn. The maximality tells you that in particular, a corollary of maximality is that if you have a subset of n, then either it belongs to you or the complement belongs to you. So note for every a either n belongs to you or complement belongs to you. And if you think of it in terms of an additive measure, then U is just a subset of n with measure 1. Then that's how we define the measure if you're given the family of sets. And to say that it's non-principal means this measure has no atom. So once we have an ultrafilter, non-principal ultrafilter, we can take ultra products. So suppose Dn is a sequence of groups. For example, and then An, inside Dn, a sequence of k approximate subgroups, finite subsets. Of k approximate subgroups. In Dn. Then you can form the ultra product G, ultra product of the G. So what is it? It's the quotient of the Cartesian product of the G by an equivalence relation where you identify two sequences if the set of n's where they coincide belongs to the ultrafilter. Okay, so sometimes we say almost everywhere. Almost everywhere means that set of n's where this happens is large, so has measure 1, or belongs to the ultrafilter. Okay, so this is the notation product, ultra product.
I have a question.
Yeah.
Does the result do isomorphism type depend on the ultrafilter?
Yes,
How about
it does. Fortunately, everything we're going to talk about will depend.
Right.
But yeah. So okay, so the nice thing about ultrafilters is that they can transfer first order properties of a sequence of objects to the other product, and it's vice versa. So this is called Law's theorem in logic, but in each concrete case, you can just convince yourself, just like reproving it in the case that you consider. So, but let me state it. So for any sentence, say in first order logic, So it's, okay, the sentence has quantifiers and operations. So for example, I'll give some examples. So let's say in the language of groups, so 5 holds for G, the H product, you can only 5 holds for Gn almost everywhere, namely the set of n's where 5 holds belongs to the outer filter. So okay, so some examples. So let xn in Gn be a finite subset, and let x be the L product with xn. Okay, so to say that all xn's have the same cardinality, or almost everywhere the same cardinality, is passes to the true limit. So to say that x, so given an integer k, say that x has cardinality k is equivalent to say that xn has cardinality k almost everywhere. So that's the first thing to convince yourself of. So, because of course it's not true for the Cartesian product, right? The Cartesian product of sets of size k is infinite. How many ways to take sequences? But the fact that we have an ultrafilter tells you that actually there are only k equivalence classes. Okay, so the point is that if you take, let's say, x of xn is like that, Gn, then you let AI be the equivalence class of this sequence. And it belongs to x. And you see that for every x in capital X, so x is the sequence xn, then in fact x is equal to one of them, is equivalent to one of them, because if you let, for each I, you let set of n's, such that xn is equal to a n I, it forms a partition of n. So one and only one of the Fi belongs to u. Okay, so this means that for this, say, Fi nodes belongs to u, this means that x is equal, the sequence xn is equivalent to the sequence AI. Okay, so that's one instance of Losch's theorem. Because having cardinality k is a sentence in first order version. You have k elements, they are distinct, and you don't have more than k. Okay, so maybe, another example is to be a subgroup or to be closed under multiplication. To say that, okay, so clearly G becomes, first of all, G becomes a group. Okay. So you can multiply sequences. Okay, so second, to say that x squared is containing x is again equivalent to say that x squared n is containing xn almost everywhere. So for the same reason, to say that x is a subgroup is equivalent to say that xn is a subgroup almost everywhere. And what matters for us is to say that x is a k-approximate subgroup. Is equivalent to say that xn is the k-approximate subgroup almost everywhere. So here I fix k, very important, fix k, but I take sequence of xn to say that the alter product is k-approximate means, if you unfold the definition, it means that x squared is contained inside x times a union, let's say, 1 to capital K of translates of x, but there are only k translates, it's fixed. So if I unfold this this property for the alter product, I see that it exactly means that each xn is a k-approximate subgroup. Okay. Okay, so just with one difference, which is that usually here I will consider finite subsets xn of G, but when I take the alter product of finite subsets, if the cardinality is not fixed, the alter product is not finite. So this x typically will not be a finite set. It will be what's called a pseudo-finite set, the alter product of finite sets. But it will still have the k-approximate subgroup property. It still have this property, this covering property. If n and gn are finite k-approximate subgroups, then the alter product of n is still k-approximate subgroup, but it's not finite anymore necessarily. I mean, it's finite if and only if there is an upper bound on the size of all n. Current k-approximate subgroup of the product G, and which is pseudo-finite. So that's the definition. Pseudo-finite means alpha product of finite. So then we can reformulate the theorem in terms in these alter products settings. So the theorem, the main theorem is equivalent to the theorem prime, but if n is a pseudo-finite K approximate subgroup of 2, then there exist I forgot to say one thing. The subsets of the form, subsets of G of the form, which are ultra products of sets Xn, are called internal subsets. So I'm going to reformulate the theorem. So then there exists M, normal in H, subgroup of G. So internal subgroups such that M is nilpotent. H mod M is pseudo-finite, and A is contained inside H times X, where X is finite. So that's the ultra product reformulation, yes.
So at the very beginning, we had a formulation of cardinalities.
Right, and then I said...
we went to equivalent form K approximate, but now on the level of filter product, it's not anymore equivalent, right?
It is. So I went to a formulation in terms of cardinalities to a formulation in terms of containment inside few cosets of subgroup, and then I said the theorem is still, it's enough to prove the theorem for approximate groups. Okay.
Right. My question is that now if I'm just on the level of filter products, there is no such equivalence anymore. That K approximate and on the level of cardinalities. Because your cardinalities will not.
So, yeah, I mean, the cardinalities will be pseudo-finite cardinalities.
Okay.
So you can.
So there is some equivalence, but.
That's just right. I mean, you can talk about the cardinality of bold A. It will be an element in the ultra product of the integers.
Okay.
The ultra power of the integers. So the non-standard limit. Okay. And so you see one point which is worth mentioning here is that here I say that A is contained in finitely many cosets of H. I don't say that there is a bound in terms of K. You say it's finitely many. But what it implies is that at the level, because everything is internal, it implies that the sequence of AN will be contained in finitely many cosets of this HN. And this finitely many, the number will be bounded by this number here. And so, because this is true for if this is true for any ultra product and any sequence of approximate groups, this implies that there is a bound, uniform bound, depending only on K. Because if not, well, you could find a sequence of approximate groups where you cannot find such a, you can never find Mn and Hn satisfying these properties, and then you will violate, taking the ultra product, you will violate the finiteness. Okay. So So that's why the theorem is not constructive. It does not give you a bound on the C of K, on the proportion of the coset of this nilpotent group, which does not give you this bound because we're going to prove this theorem, and this is just with some finite. We will tell you that this is contains a finite number of cosets. It does not give you a bound on this finite. You could say the same thing actually for the nilpotency class here. I'm just saying it's nilpotent. But we'll see that in the proof we'll in fact prove that the nilpotency class is bounded in terms of K only explicitly. Okay, so let me pass to Hrushovski view model. Okay, so here's the theorem. So let A in G be a pseudo-finite in approximate assembly. Again, of a symmetric product of groups. Then there is a locally compact group. A nice group that we are used to consider, the locally compact group G, and the homomorphism, group homomorphism. Pi. From the subgroup denoted by A to G, in fact surjective, such that, first of all, the image of A squared is a compact neighborhood of the identity. And second, you can approximate the topology by internal sets. So for every K inside U in G, K compact, and U open, you can find internal subsets in A, such that pi inverse of K is contained in X, containing pi inverse of U. So maybe this might be controlled. For every containing new A compact, new open G, in fact, there exists, to be more precise, there exists an integer K, and X inside edge of K, internal, such that the image of the compacts and the open sets satisfy this. So you can, if K, if K is very close to U, then it means that in between you can find an internal set. So the topology is given by, I mean, is controlled by internal sets. So, some remarks. So you see from this theorem that the kernel, the kernel of phi, so phi inverse of 1, is contained inside some a to the k0. Some k0. So this means in particular that this phi is essentially, I mean, it's in some sense it's almost injective. The kernel is small. The kernel is contained in the ball of Freddy's K0 in the generality set A. It's a homomorphism between the group generated by A and some local constant group. And the kernel is bounded in A to K0. So the phi is somehow almost injective. So in that sense, pi and g are a model of A, model of the group generated by A. So in fact, we'll see that in the proof, we'll get K0, which is 4 for the kernel. Kernel is actually contained A to the 4. Another simple remark is that G must be unimodular. Because on this group, there is a measure which you can take, which is the counting measure, which you can renormalize by the size of an and take the ultra limit. And when you do this, you obtain a measure on G, because pi of a squared is a compact neighborhood of 1. You can renormalize so that an squared has measure 1. So you have a counting measure which will renormalize its probability on an squared. And when you take the ultra limit, you get a measure on G, which gives measure 1 to a neighborhood of the density. But this measure is its counting measure on Gn, so this measure is left invariant, right invariant. So when you go to the ultra limit and you apply pi, it must also be left and right invariant. So the image under pi.
It's clear that it's sigma additive when you take an ultra limit
it will be sigma additive in the image. Yeah, that's right. It's renormalized. diagram. And so it's not any group that appears. And in fact, in the proof, not today, but later, eventually, the proof will show that you can take G, that G has an open subgroup let's say G prime, which is of the form K times L, where K is compact, and L is a nilpotent simply connected group. So once we will have shown this, it will be almost the end of the proof. But,
Don't get all the compact Lie groups, for instance.
Can we get all the compact groups? I don't think so. Yeah, I don't think you can get. I need to think. I don't think so. Okay, so another remark. What happens if G is trivial? What if G is just the rest? So in this case, what does the theorem say? So the theorem says that the kernel of phi is an internal set. So the kernel of phi is contained in A to the K0. But if G is trivial, the kernel of phi is all of the group generated by A. So this means that A to the K0 is a subgroup. And if A to the K0 is a subgroup, this means that for almost every n, the n to the K0 is a subgroup. So almost everywhere, if n to the K0, let's call it K sub n, is a subgroup. Okay, but because of the K approximate group property, we can see that K sub n is less than K to the power of K0 of an. Okay, because we see that Kn is contained inside x xn to the K0 an. This is the xn from the definition of K approximate group. From the definition of assuming an is a K approximate group. So what this means is that there is a subgroup, a finite group. Okay, an is finite, so that's a finite subgroup, which contains an, and which is not much bigger than an. It's less than K to the K0. So in this situation, we can say we are done. We've proven the theorem. Okay, the main theorem. In this situation, if G is trivial, then we are finished because we showed that showed that AN is contained in a finite group, which is actually not much bigger than AN itself. And so we are done.
But you wanted to say something about me?
So here there is, if G is trivial, there is no nilpotency going on. It means that your approximate group, your sequence of approximate groups, is controlled by a subgroup, genuine subgroup. Okay. So actually, the same holds if G is compact. If G is compact, the same conclusion holds. Because you can take K equals U in the Hrushovski's theorem, and you get that pi inverse of G is contained inside A to the K0, and so you again get that A to the K0 is a subgroup. And you're done. This means that your sequence of approximate groups, AN, is contained in a finite group, which is itself, and is a positive proportion of this finite group. So it's a large, so this finite group is not much bigger than the approximate group. So that's the same thing. So what if G has a compact open subgroup? Well, I claim that the situation is slightly more complicated, but it's still, we have what we want in this case. So, so in this case, the point is that by by A, pi of A squared is a compact neighborhood of the identity. A compact neighborhood of the identity in G. If G has a compact open subgroup, it must be containing infinitely many cosets of the compact open subgroup. By A, this is contained inside infinitely many cosets. Okay, this is an open bracket. And then for the same reason, you're going to get that inverse of H is integral and containing some A to the K0. And so the conclusion will be that there exists some Kn, finite subgroup, in the end with Kn less than A to the K naught An, and Kn contained in some Xn Kn, where Xn is bounded. So Xn is bounded by what? By some L, which is the size of this finite number of cosets. So you see here that the difference between what we had before in this case is that we are using the property of the limit space G, that is has a compact open subgroup, and the fact that it's well known that when you have, because this is if this is compact, then every compact set is is contained in finite union of infinite number of cosets of open of H, because H is open. But this finite here, you don't have a control on in terms of K on the cardinality of X. You just know it's finite because that's the property of locally compact groups and the topology that H is open. But you don't have a control. So the only thing you will be able to say is that there exists some L which may depend on which depends only on K, but you don't know how, with this property. And so again, in this situation, this means that your sequence of approximate groups is controlled by a finite group. An is contained in a bounded number of cosets of a finite group. The finite group is not much bigger than the set itself. So, to give you an example where we are never in this situation, the simple example is when we take an to be minus n minus n inside Z. Okay, so this is an arithmetic progression. An plus an is contained in two copies of an, two cross sets of an. Okay, but you're never in this situation. There is no finite subgroup which a few cosets of which contain an. Only finite subgroup of Z is 0. So you cannot cover an by boundedly many transets of K. And so this means that in this situation, when you do the theorem, you apply the Hrushovski Lie model theorem, the Lie group, the locally compact group D that you get, does not contain a compact open subgroup, and indeed you see that there will be one parameter subgroup R. There will be R. We see from the construction that so to conclude this set of remarks, let me say that let me prove what I told you at the beginning, namely that we can now show that if you have a sequence of approximate groups in a group with bounded exponents, then they must be controlled by a finite subgroup. So you get the following corollary. This is super successful. So given K and E, natural numbers, if G is a group of exponents E, and K approximates finite subsets, finite subgroup. Of G, so it's a finite set satisfying its properties of P times K. Then there is this H in G, finite subgroup, and there's this X, a subset of G, of bounded size, and this bound depends only on K and E, such that A is contained inside H, and H is at most C times H, same C. this is a complete, as far as I'm concerned, classification of approximate subgroups of a group of finite exponents. So if you have a group of finite exponents, K approximate subgroup of it, then it's controlled, in that sense, by a finite group. So there's a finite subgroup, not much bigger than A, which contains A up to a finite bounded number of translates. And the proof, so the proof, well, the proof is, again, to show this, it's enough to prove the same statement for ultra approximate groups, for pseudo-finite approximate groups. And so you can write the same statement for pseudo-finite approximate groups. You start with the pseudo-finite approximate groups, you apply the Hrushovski model theorem. So you have this map from functional group A to G. G is a locally compact group. But now, it's a subjective homomorphism. Now this subgroup here has exponent E, because I agree on that. Because that's how I started to take sequence of approximate subgroups in groups of exponent E. So this has exponent E. So G has exponent E. So we have a locally compact group of exponent E, which implies that G must be totally disconnected. If there is some connected component, it cannot finite exponent. It would be elements of infinite order. So G has exponent E implies that G is totally disconnected. Okay, and it's well known that totally disconnected groups have a compact open subgroup. So we have a compact open subgroup H. Theorem. So we are back in this situation, compact open subgroup, and we have the conclusion. Okay. So now, what about the proof of the model theorem? So yeah. So I said D model theorem, but there is a for the moment there is only a locally compact group. There's no lead group. There will be a lead group. But to get it, we'll apply a solution to the Hilbert's fifth problem. We will apply this Yamabe theorem. So I'm going to talk about this next week, this Yamabe theorem. So for the moment, I'm happy with just showing that there is a locally compact. There is a homomorphism to a locally compact group. Okay, so the proof of Hrushovski. Okay, so you see this theorem. So okay, so we have a statement. We have a pseudo-finite approximate group. Okay, approximate subgroup. And then there is this I. G, the G totally compact. these nice properties that 5a squared is compact neighborhood, and we know that this approximation so what we need to do, really, so G will be the quotient of the group generated by a certain so what this theorem tells you is you can find a topology on A, on the group generated by A, which is locally compact. Except this topology may not be Hausdorff. But once you found this locally compact topology, you can quotient by the closure of the identity, and you'll get a Hausdorff locally compact. Okay? So another way to phrase this theorem is to say that we are going to build a locally compact topology on A. Okay, but so what does it mean? So we need to find a topology on this pseudo-finite approximate group that we are just given. We just started with just a sequence of arbitrary groups with no topology anywhere. The only thing we are given is this collection of finite sets and with this k-approximate property. So we need to be able to, so what is a topology? We need to be able to say when is an element close to the identity. Right? So we need to be able to define what it means for an element of AN to be close to the identity. Okay, so this is what it's about. And so the key behind this, I tell you intuitively what's the idea. The idea is you have this finite set A, and the only thing you know is A times A is containing K times A. One contains identity, it's symmetric. Okay, but it could be pretty arbitrary. So you'd like to say that an element is close to the identity. Well, you don't have so much choices, but one thing that comes to mind is you could look at an element G in the group generated by A, and say, look at the translates of A by G, and look at the symmetric difference with A. So is it going to, so when you translate it, is it going to be to translate A far from A, or is it going to have a large intersection with A? So you'd like to say that G is close to the identity if this symmetric difference is small. And since you have nothing else but cardinality, these sets are, there's no topology, it's just discrete groups. So the only thing you could say is to say that this is small. But small means it is less than epsilon A. So that's the intuition, how to get the topology out of just the approximate group. So, of course, so this makes some sense for every given A, but topology would only make sense in the in the algebraic product. Okay, so so that might give you a topology, but you need to show it's locally compact. Okay, so the key behind all of this is the following lemma. Which is independently due to Hrushovski and to Thompson with very different proofs. And there is yet another group called CSAC. So this lemma allows you to, so it's a very fundamental property of approximate proofs. It allows you to find a certain fine structure inside the approximate. So let me be more precise. So it says the following, that given the integers, let A be define it. So inside some ambient history, then so it is the subset S, which you can find in A to the 4, such that S to the K is still contained in A to the 4, and S is a positive proportion of okay, so it means that given any approximate group, right, there is a candidate for this neighborhood at the S, such that if you take its powers, kth power, you remain in S, you remain in A, or in A to the 4. And, okay, so there is such a set, but the point is that the set is not too small. It's a positive proportion. Okay. So this is a combinatorial lemma. Hrushovski's proof is very different. It's more theoretic. I cannot say that I still don't understand it well. But these two proofs are very elementary and constructive. They are constructive as well. So let's assume this lemma, and let's see how to build it. The idea is to say, you do this, so in n to the 4, you apply the lemma, and you get some sets. Such that every time S and K is some positive proportion of Kn, Sn K to the power K, something in, and you can, iterating the lemma twice, you can assume that S n K plus 1 is, let's say, square, I'm saying S and K. Okay, once you have such an S, you can apply the lemma to S instead of A, and then you get a small set, still a positive proportion. So you can assume this. You can do slightly more. Here you can add. You know, if you have a subgroup of finite index in a group, then it has a normal subgroup of finite index, right? And if you intersect finitely many sets of finite index, it still has finite index. So here, the same phenomenon happens. You can assume that S is normal in the sense that A times A inverse, or every A. Okay, because S is a positive proportion, so the same argument tells you that you can somehow make it almost normal in that sense. So you can just add this assumption here. And then you let S of K be the product of the S and K. And so the thing that you need to check, essentially straightforward, is that the SNK, the SK form the basis of neighborhood of the identity. And so this is the basis for your deployment. And so you let gamma be the intersection of the SK. And that's going to be normal subgroup. So yeah, the point is that this intersection is a group, is a subgroup, because of this one. Subgroup, which is normal. Okay, and so so now you need to show the properties that A modulo gamma is compact, and it's a neighborhood of the identity. So it's a neighborhood. A is a neighborhood of the identity because it contains SK, and SK is your basis. So that's easy. But the fact that A is compact follows somehow from the completeness of products. So it's a small exercise to see that A must be compact. And then this the third property is also clear once you set things like that. So I'm going to stop now. I'm not going to prove this lemma. This lemma can be proven in at least 3 different ways. But you can. I just tell you what the set is. So if you take the proof of these guys, you take this set. So it's almost what I said with the symmetry difference, but it turns out that the analysis is easier if you look at convolution norms and the convolution of A with itself smoothes things out a bit. And so if you take this set, then obviously this set contains the identity, it's a symmetric set, and these properties are easy to S to the K, S epsilon to the 1 over epsilon is contained A to the 4. Because whenever this is strictly less than this norm, this means that the support of these two functions is the two supports intersect, which means that G belongs to A to the 4. So that's and so the key property, of course, to prove is that S epsilon is positive proportion of A.
So for to be a basis of topology, what is needed?
Well, you need
What do you need to check there?
finite intersection,
Yeah.
and then you have a group, so you know everything. You look at translates, any translation is SK. But well, yeah, so that's it. And, but yeah, you need to show that A is compact. So to be more precise, you need to show that A gamma is compact. So you need to show that, for example, to show that A gamma is closed, you need to show that the intersection of A is equal to A gamma. That's to show that A is closed in the projection modulo gamma. And this, yeah, and there it's key that you have an ultra product and somehow there is a automatic completeness of ultra products, which helps you to show that. Model theorists have a way a much more conceptual way to phrase all of this, which is very powerful. So for them, it's called the logic topology. And it's automatically really compact. And it follows from the compactness theorem. First order logic. But in order to so yeah, for if you're interested in reading about this, I mean, in this language, I encourage you to look at the Bulbaki Semyon on dependencies, which is a very good, very short and excellent introduction to this language, to this theorem.
This, although elementary, it seems to be a crucial step in the argument. Right.
This lemma.
Yes.
This is a crucial.
But for model theorists, it was obvious.
No. So this lemma was not obvious at all. So this is, in fact, a significant part of Hrushovski's paper. And but what's obvious is the fact that once you have this sequence of sets, SK, then you get a locally compact topology. You see somehow that local compactness comes from the covering property. It comes because you see that these SKs, I mean, they form a basis of neighborhoods of the identity, and your topology is totally bounded with respect to these SKs, in the sense that you see that A is always about a finite number of cosets of SK. SK is a positive proportion of A. So A can be covered by a bounded number, bounded in terms of cosets of SK. So this is the total boundedness property. Any ball can be, or any compact set can be covered by boundedly many balls of small radius. So here, what plays a role is the balls of small radius, or these SKs, K is large.